Welcome back to the 8.3 video part 2. That was AC/DC with Back in Black. And we're going to go ahead and get started today talking about simplifying radicals. And we're finally going to figure out why on earth I played that happy birthday song in the last video. So to help us simplify radicals, these larger radicals we've been talking about, the cubed roots and the fifth roots, we're going to talk about something called the birthday cake method. And these are a little bit more tricky. They're not as easy as the square roots we've been talking about because they are a higher root. They're a cubed root or a fifth root or a fourth root. So we have to do something a little bit different because they're not square roots like the ones we've been talking about before. So for us to do this birthday cake method, we need to kind of revisit the idea of a prime number. Now, it's been a while since we've talked about primes or since you've heard about primes, but just as a refresher, a prime number is a number that only has factors of 1 in itself. So in other words, the number 2 only has factors of 1 and 2. The only two numbers you can multiply together to get 2 are 1 and 2. Same thing with number 3. The only numbers that multiply together to get 3 are 3 and 1. The only numbers that multiply together to get 5 are 1 and 5. 7, we have 1 and 7. Times. And 11, we have 1 times 11. And we could keep going, okay? There are many other prime numbers. Actually, there's an infinite amount of prime numbers, but in order for us to do this birthday cake method, we're probably just going to focus on these 5 right here. They're not going to get much bigger than 11. So if you can remember these 5 prime numbers, you're going to be golden. All right, so let's talk about what this birthday cake method is. To help us simplify these radicals, the ones we've been doing so far have simplified to a whole number, and that's what's been making it kind of nice for us. But we know that some of these might not actually simplify to a whole number. There might be some leftovers or leftover numbers inside the radical symbol when we're done simplifying, just like we had with the square roots. Not everything actually simplified. So let's talk about the cubed root of 135. How this birthday cake method works is we start with the inside number. Okay, in this case it's 135. And we're going to pick a prime number that evenly goes into 135. So just looking at these 5 numbers right here, I can probably guess that 5 goes into 135 because after all 135 ends in a 5, so it should be divisible by 5. So just like a regular division problem, okay, we're going to do 135 divided by 5. Now 5 goes into 135 27 times. So just like a division problem, we would put our answer up top. But what we want to do is continue this process. Okay, we're going to kind of build what's basically going to turn into something like a birthday cake. If I try to find another prime number, this time I want to look at the number 27. So looking at 2, 3, 5, 7, 11, one of these prime numbers that can go into 27 would be 3. 3 goes into 27 9 times. So I would put that above my division bar, and I'm going to continue the process. Another prime number that goes into 9 is 3. 3 goes into 9 3 times. Keep going. Another prime number that can go into 3 is 3. And 3 goes into 3 once. Okay, so we're left over with this number 1. And just like a birthday cake, why it's called the birthday cake method is because we always want a candle on the top of our birthday cake. So what's really important about going through these other examples is that your cake, your stack here, always ends in a candle. You always want the number 1 up top. And you can kind of notice it looks like a birthday cake or a wedding cake where you have the largest amount on the bottom, and then it gets a little bit smaller, a little bit smaller, a little bit smaller, until you have your candle up top. All right, so it starts to look like a birthday cake. What we do, though, is that since this particular root is a cube root, the number 3, we want to take a look at these prime numbers on the left-hand side and make a group of 3 identical numbers. And what I mean by that is if you take a look at 5, 3, 3, and 3, I can make a group of 3 numbers that look exactly the same. Okay, so I'm grouping these 3 numbers together because this little root right here is telling me I need a group of 3. So since I made one group of 3, I am able to pull a 3 out of the radical. It's almost like it comes out. I can pull the number 3 out. But notice how I did not group this number 5 with anything. I wasn't able to group it with any other numbers. So this 5 is left inside that radical symbol. So we are left with the cubed root of 5. So I was able to pull a 3 out according to this group, but I still had a 5 left over. All right, so let's take a look at the next one. Our inside number is negative 81. And we want to try to break this down. What's different about this one is that we actually have a negative inside number. Okay, this one happened to be positive. So this is going to act just a little bit different. Instead of using positive primes on this left-hand side like we did over here, we're going to use negative primes because this is a negative inside number. So one of these prime numbers that can go into 81 is 3, but since my inside number is negative, I'm going to divide by negative 3. Negative 81 divided by negative 3 gives me a positive 27. Another prime number that can go into 27 is 3, but again, since my original number was negative, I'm going to divide by negative 3. 27 divided by negative 3 gives me a negative 9. Remember, I'm trying to reach this candle. I want a 1 at the very end. Another prime number that can go into 9 is 3. But I need it to be negative because our first number was negative. Negative 9 divided by negative 3 gives me a positive 3. If I keep going, I'm not done yet, I want that candle. Another prime number that can go into 3 is 3. So I'm going to make that negative 3. 3 divided by negative 3 is negative 1. All right, now some of us might think we're done right now, okay, because we have the number 1 up top, but we're not. Okay, we want a candle, a positive candle after all. So we got to do one more step. Okay, if I want to try to get a positive 1 up here, okay, this is my goal. I want to try to get a positive 1 candle. I need to divide negative 1 by something to get a positive 1. In order to get a negative 1 to be a positive 1, I need to divide it by a negative number, in this case, negative 1. Okay, so negative 1 divided by negative 1 gives me my positive 1 candle. If I take a look at my root, okay, my root is 3, so I want to make a group of 3 identical numbers. So maybe I'll circle these 3 identical numbers right there. Okay, so I can pull a negative 3 out, okay, because I was able to make one group. I can pull one negative 3 out, but I am left with, inside my radical, a negative 3 and a negative 1. If I were to multiply those together, negative 3, negative 1 would give me a positive 3. Okay, but we got to be careful because this is just how this cube root simplifies. We still have that negative 8 out front that we started with. So we're going to take negative 8 times negative 3, which gives me 24, and I am left with the cubed root of 3. Okay, so this birthday cake method, we always want a candle, a positive candle at the very top. And in this case, since our beginning number was negative, we want all of our primes to be negative. All right, let's try one that's a little bit more involved. We're going to start with 192. And we want to find a prime number that goes into 192. Since it's even, okay, maybe we'll use 2. And we don't have to worry about negatives this time because after all this number is positive, so we'll use positive 2. 192 divided by 2 gives me 96. If I think of another prime number, maybe 2 would work again. 96 divided by 2 gives me 48. 48 divided by 2 gives me 24. 24 divided by 2 gives me 12. 12 divided by 2 gives me 6. 6 divided by 2 gives me 3. And then another prime number, 3 divided by 3 gives me my candle that I'm looking for, the number 1. All right. So this time my root is 5. I want to make a group of 5 identical numbers. 1, 2, 3, 4, 5. Here are 5 identical numbers. So I'm able to pull a 2 out of this radical. So I'm going to put that out front. But since I was not able to group these, I still have a 2 and a 3 left over. Those are still on the inside of my radical. If I take 2 times 3, I get 6. So I was able to pull a 2 out because I made one group, but I have a 2 and a 3 left over, so that gives me a 6. Now, what also makes this one a little bit more complicated is this time we have a variable. Okay, so we have a to the 6, which means we have 6 A's. I almost said X's because we're used to X's, but we have A's this time. All right, so 1, 2, 3, 4, 5, 6. Okay, so just like we do these numbers, I want to make a group of 5 identical variables. So 1, 2, 3, 4, 5. There's a group of 5 identical variables. Since I made one group, I can pull one A out, so I can go out front with my 2. But I was not able to group this one, so it is still left inside the radical where the original A's began. So there's how we can simplify the third one. All right, let's take a look at some operations with these higher roots. Okay, maybe we'll multiply some cube roots or divide some fourth roots. Just like we talked about with square roots, the same ideas apply here. We can multiply the inside 12 by the inside 18. So 12 times 18 can give me 216. But I need to keep that cube root that both of them had, so we'd have the cube root of 13. Now, most of us, maybe by now, already know what this is, because in the last section we talked about what number to the third power would give me 216, and most of us, you might be thinking that number would be 6. Okay, so some of us know that off the top of our head, but just in case you weren't sure, you could use the birthday cake method on this 216, and let's actually do that and see if we get 6. If I want to break down 216, okay, a prime number that goes into 216 is 2, and I'm left over with 108. Another prime number would be 2. We have 54. Another prime number 2 would give me 27. Prime number of 3 would give me 9. Prime number of 3 would give me 3. And then prime number of 3 would give me 1. Okay, so there's my birthday candle. According to this root, I want to make groups of 3 identical numbers. So if I take a look at my birthday cake here, my prime numbers, here's 3 identical numbers, so I can take out a 2. Here's 3 identical numbers, so I can take out a 3. And notice how we circled everything. There really isn't anything left over. There's not an extra number up top or in the bottom. Okay, we circled every single prime number. So if I pull out a 2 and I pull out a 3, 2 times 3 would give me 6. And since I didn't have anything left over, I don't need a cubed root anywhere in my answer. So most of us might know this by now, but just in case you don't, you could use the birthday cake method to break it down and still get the same answer. All right, let's try this one. The fourth root of 5 and the fourth root of 80, maybe we can break down 80. Okay, like we did over here on the 216. We couldn't really break down 5 because if you remember, 5 is one of our prime numbers. Okay, so it really isn't going to break down. Prime number that goes into 80 is 2, and we're left with 40. Another prime number is 2, and we have 20. Another 2 gives us 10. Another 2 gives us 5. And then a 5 prime number would give me my candle of 1. Okay, so I want to make a group of 4 identical numbers, 1, 2, 3, 4. So I can pull out a 2 because I was able to group them together, but I still have a fourth root of 5 left over. Now, since we have a fourth root of 5 in the denominator, notice how we have something up top that's exactly the same as the bottom, so these cancel, and all we're left with is the number 2. Okay, so just like we simplified square roots before, we're simplifying these higher roots. We just have a different way of doing it. Okay, we're going to use the birthday cake method instead of trying to find those perfect squares. Alright, let's check out a few more before I let you go off and try some on your own. In this case, we're dealing with subtraction, and we know we can only add and subtract radicals when they're exactly the same. And notice how the roots are already the same. Okay, so that's one thing going for us, but the inside numbers are not the same. So let's try to break down 32 and see if we can get it to have a 2 left over at some point. So if we take 32, prime number would be 2. I'm left with 16. Another prime number of 2 would give me 8. 2 would give me 4. 2 would give me 2. And then 2 would give me 1. All right, so there's my candle. According to the root of 4, I want to make a group of 4 identical numbers. All right, so I can make one group, so I can pull a 2 out. And I did not circle this one, so that is still underneath the radical symbol. But we got to be careful because we had a 3 out front to begin with. So I can't forget that 3 out front. And I'm eventually going to multiply the 3 and the 2 together. Now this part, we can't really break down 2 because it's already a prime number. So we'll keep it the way it is. Alright, so 3 that we started with times the 2 that we took out gives us 6 fourth roots of 2. And here I'm subtracting 2 fourth roots of 2. So now that they're like radicals, same number, we can add or subtract the outside numbers. So 6 minus 2 gives us 4, and we'll keep the like radical, the fourth root of 2. All right, so there's number 10. Number 11 is the mother of all of them. Okay, we got variables, we got powers, we got big numbers, we got negatives. There's a lot of stuff going on. Let's just start with the number first. If we break down 128, prime number of 2, perhaps, would give us 64. Prime number of 2, we'd get 32. Another 2 would work. We get 16. Another 2 would give us 8. 2 would give us 4. 4 would give us 2. And then lastly 2, and there's my birthday candle of 1. Now according to the root, I need to make a group of 3 identical numbers. All right, so there's 3 identical numbers, and there's another group of 3 identical numbers. So let's keep the -5 that we started with. According to this group, I can pull out a 2. And according to this group, I can pull out another 2. But this group, or not this group rather, this number 2 was not circled. It's all by itself. It's all lonely. So it still is inside the cubed root symbol. So we have the cubed root of 2. Okay, so those are our numbers. Now let's check out the variables. I have 6 A's. So 1, 2, 3. 4, 5, 6. I want to make a group of 3 identical variables. So there's one group, and there's 2 groups. So I'm able to pull out a total of 2 A's. I was able to make 2 groups. So let's pull out 2 A's. We can say A squared. Now if we take a look at the B's, okay, I have 2 of them, a B and a B. But I want to make a group of 3, and since I only have 2, I can't make a group of those, so those 2 B's would have to stay inside that radical symbol. Okay, I can't make a group of them, so they need to stay. So let's start to simplify this. -5 times 2 would give me -10, and if I multiply by 2 again, that would give me -20. I still have the A squared out front, and my leftover radical, I have the cubed root of 2b squared. So there's 2b squared. 2b or not 2b. All right, so there's number 11. All right, so it's your turn. I want you to try this mother of a beast right there, okay, a throwback to the exponents that we talked about in the first video. And I would also like you to try this one, okay, simplifying it using the birthday cake method. See what you can take out, see what's left over, see what you get there. The bottom 2 is a review from the square roots. Okay, we said that we cannot have square roots in the denominator of a fraction. So remember, this is where you got to multiply the top and the bottom by a specific square root. All right, so give these 4 a shot. See how you do. All right, so let's check out the first one. The first thing I noticed right here, we have a bunch of stuff grouped together with parentheses. and I have a power of 3/5, a power of 6/25. Both of those are being raised to the power of 10 over 3. So according to the power to power property, we can distribute the power, or the 10 to the third, or 10/3, to both of these individual powers. So if I take 3/5 times 10 over 3, I get 30/15. Okay, remember we can do 3 times 10, which gives us 30. 5 times 3 gives us 15. Likewise, if I take 6 times 10, I get 60, and then 25 times 3, I get 75. So we can distribute the power to the other powers inside the parentheses. If I take a look at these exponents a little bit further, 30 over 15 just simplifies to 2, and 60 over 75 can simplify to 4/5. Okay, so I'm just simplifying those fractions. But we can figure out what 2 squared is. 2 times 2 gives us 4. Okay, so if I take a look at what we have 4x to the 4/5 and another 4x to the 4/5. So since this base is x and this base is x, and they happen to have the same powers, they're both 4 to the 5th, these are considered like terms. Okay, same base, same power, so we can add the outside numbers. 4 plus 4 gives me 8, and we can keep that 4/5 on the power of x. All right, if we check out the next one, we want to break apart 486. So here's my little birthday cake with my candle. I made a group of 4 identical numbers. That was 3. So I was able to take a 3 out. And since I had a 2 and a 3 left over, those stay on the inside. Together, they give me a 6. If I look at my variable, I have 6 A's. And according to my root, I want to make a group of 4 of them. Okay, so there's my group. I can pull 1 A out because I have one group. But I did not group these together, so I have 2 A's left inside, so I can write that as A squared. All right, so there's the answer for the second example. All right, review time. Okay, we cannot have a square root in the denominator. Okay, we just don't like it there. So the first thing I did, now some of you may have multiplied by the square root of 20 and the square root of 20. Okay, you can absolutely do that. Hopefully you got the same answer in the end, but I would rather work with smaller numbers. So what I did first is I broke apart 20. Okay, a perfect square that can go into 20 is 4. The other factor is 5. And I know the square root of 4 is 2. Okay, some of you are still having trouble with this. The moment you simplify a root, it loses the check mark. Okay, I still don't have that little check mark radical sign. As soon as you simplify it, you lose it. Okay, so all I have is the number 2. So I have 5 over 2, and I still have a square root in the denominator. Okay, I'm not really getting anywhere with this just yet. So notice how in this case, to get rid of the square root of 5, I just have to multiply by the square root of 5 on the top and the bottom, instead of multiplying by the square root of 20s. Okay, so we have some smaller numbers here. Multiplying fractions, I can go straight across. So 5 times square root of 5 gives me 5 square root of 5. And then 2 square roots of 5 times square root of 5 gives me 2, that outside 2, and then 5 times 5 gives me an inside 25. But we know that the square root of 25 is 5. Okay, so again, notice how I lost the check mark. I simplified this so I lose the symbol. And I have a 5 up top, a 5 on the bottom, so those can go away. I'm left with the square root of 5 over 2. And notice how there's no more square root in the denominator. That's what we're looking for. All right, so let's check out the second one. Again, instead of multiplying by the square root of 8 and the square root of 8, okay, some of you may have done that. That's completely all right. I broke apart 8 into 4 and 2, and I know the square root of 4 is 2. Okay, so I lose the check mark. And 3 times 2 gives me the 6 out front. So the denominator can simplify to 6 square roots of 2. I want to get rid of the radical. So if I want to get rid of the square root of 2, let's multiply by the square root of 2 over the square root of 2. 10 times 2 can give me a square root of 20. And then 2 times 2 can give me a square root of 4, but I still have the 6 out front. Okay, so next thing I did was I broke down 20, because a perfect square that goes into 20 is 4. So I have the square root of 4 times the square root of 5. And notice how if I have a square root of 4 up top, a square root of 4 on the bottom. Those can cancel each other out. All I'm left with is the square root of 5 over 6. And again, we no longer have that square root in the denominator, so we're good to go. Alright, so I hope we like this lesson. I think it's kind of cool. I like the birthday cake method. I think it's fun. I think it's neat how it works. So just be prepared for next class. We're going to do a little bit more practice with some exponents and some birthday cake method problems. Okay, see you later.